On October 29, 2006, Cassini aimed its infrared spectrometer at Saturn's North Pole. The pole was in winter darkness, so ordinary cameras could not see much. Infrared light could. It showed heat leaking through the clouds, and in that darkness, Cassini found a shape Voyager had seen a generation earlier, a hexagon wrapped around the top of the planet. It was roughly 29,000 kilometers across, wider than two Earths. Its edges were not a drawing on a surface. They were moving cloud bands carried by winds near 100 meters per second. 6 sides, 6 corners. A polar vortex inside it? And Cassini had only opened the northern pole in infrared. Sunlight would not fully return there until after Saturn's 2009 equinox. The question is not whether Saturn has a hexagon. It does. The question is why a gas giant's wind can hold 6 corners for decades. The evidence points to a trapped wave in a fast polar jet, but the details of why that wave takes this exact form are still unfinished. Saturn's hexagon is not a solid structure. Saturn has no solid surface at the cloud tops. The hexagon is an atmospheric pattern near the North Pole, centered around about 78 degrees north latitude. Its outline is made by a jet stream. A jet stream is a narrow river of fast wind. On Saturn, this river flows around the pole and bends into 6 broad segments instead of making a smooth circle. That is the strange part. Planetary atmospheres often make bands, vortices, waves, and spirals. A long-lived 6-sided boundary is much rarer. The shape looks geometric, but it is made of gas, clouds, temperature contrasts, and rotation. The first clear record came from the Voyager flybys in 1980 and 1981. Voyager's images of Saturn were later assembled into polar maps, and the 6-sided pattern appeared near the North Pole. Those spacecraft passed Saturn only once. They could show that the feature existed then. They could not show whether it was a temporary weather pattern or a durable part of Saturn's circulation. That mattered because storms can be brief, even on giant planets. A single sighting could have been a rare snapshot. To understand the hexagon, scientists needed to see whether the same pattern survived over Saturn seasons. Cassini supplied that test. The spacecraft entered orbit around Saturn in 2004 and stayed there for more than 13 years. At first, Saturn's North Pole was mostly dark. Infrared instruments became the way in. They could sense heat and cloud structure even without sunlight. Cassini's infrared views showed that the hexagon was still present more than 20 years after Voyager. Later, as northern spring arrived, visible light images showed the same basic outline and reflected sunlight. The details changed, clouds shifted, haze changed, small storms moved through the region, the 6-sided pattern remained. The hexagon's scale is planetary. Its span is about 29,000 kilometers. A spacecraft image can make it look like a neat cap, but the distance across it is more than twice the diameter of Earth. The winds are also extreme. The jet forming the boundary moves at roughly 100 meters per second, about 360 kilometers an hour. Around the center sits a polar vortex, a rotating storm system at the top of the planet. These numbers matter because the hexagon is not being held in place by land, oceans, or mountains. There are no continents at Saturn's cloud tops. The shape has to come from the atmosphere itself. Cassini did more than confirm the outline. Its cameras and infrared instruments mapped the hexagon at different wavelengths. Different wavelengths probe different levels and temperatures in the cloud layers. Those views showed a layered polar atmosphere. The hexagon could be traced in clouds and in temperature patterns. It was not just a color marking at the top of the haze. Cassini also watched it change with the seasons. The North Polar region appeared bluish before full spring sunlight returned, then became more golden in later years. The supported explanation is seasonal chemistry. Ultraviolet sunlight helps produce haze particles, and the polar atmosphere changed as the long Saturn winter ended. The color changed more than the geometry. That contrast is important. It shows that the visible appearance of the pole can vary while the deeper wind pattern keeps its form. The leading explanation begins with Saturn's rotation. Saturn spins once in roughly 10.5 hours. That fast rotation strongly shapes moving air. On a rotating planet, winds do not simply flow from high pressure to low pressure. They are turned sideways by the Core-E-OH-Liss effect. The result, on a giant planet, is a system of east-west jets wrapped around the globe. Near Saturn's north pole, one of those jets appears to trap a wave. A Rossby wave is a large bend in a rotating atmosphere, controlled by the planet's spin and by changes in the wind with latitude. In the hexagon, the best explanation is that the polar jet has a stable wave with 6 lobes. Laboratory tanks of rotating fluid and computer models can produce polygon-shaped jets under the right conditions. They do not prove every detail of Saturn's case, but they show that sharp-looking geometry can emerge from ordinary fluid motion on a rotating world. The broad answer is supported. Saturn's hexagon is a persistent wave pattern in a fast polar jet stream. It is weather, but weather on a scale and duration unlike weather on Earth. The unsettled part is the exact recipe. Scientists still test how deep the jet extends, how the wave stays locked for so long, and why the stable pattern has 6 sides rather than 5 or 7. The answer likely depends on the jet's speed, its width, the wind shear around it, and the structure of Saturn's atmosphere below the visible clouds. The hexagon shows that the outer solar system is not a collection of frozen, quiet worlds. Giant planets have atmospheres that can organize themselves into long-lived machines, bands, vortices, polar storms, and in one case, a 6-sided river of wind. The shape is not artificial and it is not impossible. It is a visible edge of a deeper circulation system, one that Saturn has kept running since at least the Voyager era, and one whose exact physics is still being measured. That's why source. If this was worth your time, like it, share it, and tell me in the comments what you want to examine next. If you would like to support this work, the Patreon link is in the description.